So before I get into today's problem, I have noticed that quite a few people have started watching my videos, and I want to thank everyone who has, and I really do appreciate the support. Furthermore, if you really enjoy my videos or if you feel like my videos have helped you in some way, please make sure to share them with friends and family doing differential calculus or doing Maths 130. I really do enjoy doing these videos and it helps everyone learn, so it's a win-win for everybody. Okay, so let's get into today's problem from the 2019 June examination. And I have drawn the diagram already on the right hand side, as you can see, and I'm gonna go through each bit of the information piece by piece and relate it to my diagram so that you can understand it to the best extent. So it says a ladder 5 meters long rests against a vertical wall. Okay, so we have my vertical wall here denoted by Y. And if you think a bit further, if we have a wall and a ladder resting against it, then we are going to have a horizontal ground. And this looks awfully similar to an XY axis, in which it is. So you can assume that this is going to be perpendicular. So we have our right angle. Okay, and it says a ladder 5 meters. So here we have our ladder, and that's going to be 5 meters. Also, I've denoted the ground by X. So it just looks like an normal XY axis, so don't get confused. Okay, so the next bit of the information says if the bottom of the ladder slides away from the wall at a rate of 1 meters a second. Okay, so before we even think about any of that, let's think about a ladder sliding away from a wall. So if this ladder had to slide away from this wall, then my new position on the x-axis would be somewhere around there, and then that would mean that my ladder would be sliding down on the y-axis. So my new position on the y-axis would be somewhere around there, arbitrarily. And if it had to slide down even more, then we can assume that, let's say, it slid until there, and then of course on the y-axis it's going to be sliding down. So it looks a bit weird, but you get the idea. As it's sliding away from the wall, it's going to be sliding more down, and until it gets to a point where, well, the ladder would be completely parallel to the x-axis, if you could see it. When it's done sliding all the way down, it would be completely parallel to the x-axis and it would be lying on the floor. Okay, so let's go back to our information. So if the bottom of the ladder slides away from the wall at a rate of 1 meter a second, so the bottom of my ladder is sliding away at 1 meter a second. So we have our first piece of given information, which is a rate of change. So we can say, okay, the rate of change of the bottom of the ladder with respect to time is moving at, no, that says 1 meters a second. Okay, cool. So that just means that this is sliding away every second at 1 meter. So it's going to be 1, 1, 1, or whatever. You get the idea. So they want to know how fast is the top of the ladder sliding down the wall. So here's the top of the ladder, and as I explained before, as this is sliding away, this is going to be sliding down. So they want to know how fast is this sliding down when the bottom of the ladder is at 3 meters. So let's arbitrarily say that this is 3 meters away from the wall, and then we can say that's the position. So let's say this is 3 meters away from the wall, and it's sliding away at this rate, and all they want to know is how fast is this part sliding down. So let's get into the solution. So notice that we have a right angle triangle. So we can make our general equation from this right angle triangle. So I'm going to say, okay, y squared plus x squared is going to be equal to 5 squared. And that's going to be because of Pythagoras. Now let's look at this equation that we have. What are we interested in? We are interested in our y variable. Why? Because our y variable is the one that they're asking the rate of change for. How fast is the top of the ladder sliding down? That's what they want to know. How fast is this sliding down when x is 3 meters away and at this rate of change? So let's isolate my y variable, because that is what I'm interested in. So y squared is going to be equal to, this is going to be 25 minus x squared, and taking the root of both sides, I get that y is then equal to the root of 25 minus x squared. Okay, so now we can also write this, well, because we're going to take the derivative of it, we can write this as 25 minus x squared raised to the half power, because this is power over root. This is just exponent laws. So let's take the derivative of both sides. So we're going to say d over dt of y, and that's going to be equal to d over dt of, I'm going to write it as this one, so 25, oops, that is ugly, minus x squared and raised to the half power. Okay, deriving the left hand side, we have dy dt, which means the rate of change of y with respect to time, which is exactly what we're looking for, because we want to know how fast this is sliding down. So taking the derivative of the right hand side by using chain rule, we're going to move this one to the front. So if I do that, it's going to be half, copy whatever's in the bracket, and then minus 1 from the exponent, and then we're going to multiply by the derivative of the inside. So if I take the derivative of the inside of the bracket, derivative of 25 is going to be 0, then the derivative of minus x squared is going to be minus 2x, and then we are taking the derivative with respect to time, so we're going to say times dx by dt. Okay, so far so good. So we can simplify this by saying, okay, I'm going to multiply this by that fraction. So if I do that, I can say, okay, minus 2x multiplied by dx by dt, and then notice that I have a negative exponent. So by using exponent laws, I can move that term to the bottom. So if I do that, I'm going to have all over 2 into 25 minus x squared, and you take the root of that by using power over root again and negative exponents. Okay. Now we have dx by dt in our expression, and we have a dx by dt which is given, so we know that dx over dt is changing at 1 meter a second, so we can sub that in. So this is just going to be minus 2x all over 2 into 25 minus x squared, and we're going to root that. So now let's not forget what we found right here. This is an expression which tells us how fast y is changing, or in other words, how fast is y sliding down. And now by subbing in our dx by dt, we have an expression which tells us how fast y is sliding down when x is sliding away at 1 or 1 meters a second. Okay, so they want to know how fast is the top of the ladder sliding down, or in other words, how fast is y sliding down when the bottom of the ladder is 3 meters from the wall, or in other words, when x is 3 meters away from the wall. So somewhere around there, whatever. So we have given that x is going to be 3, so we can sub in 3. So by doing that, we can say minus 2 into 3 and 2 into 25 minus 3 squared, all rooted. Then simplifying that more, okay, that's minus 6. 2 into the root of that's going to be 25 minus 9, that's going to be 16. Then simplifying that even more, we get that that's going to be 2 into root of 16 will be 4. And we're going to come down here and multiply 2 by 4, we'll get 8. And simplifying that one more time, we can say that that's minus 3 over 4. And how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 3 meters from the wall, and additionally the bottom of the ladder is sliding away at this rate? Well, the top of the ladder is sliding down at minus 3 over 4 meters a second.